Teste. Fala comigo, Giovana. Fala comigo. Agora ver se rola interferência quando eu ligar o outro.
Ok.
Правда у меня не говно в задача на презентации? Почему у меня не работает? Ну не знаю, сейчас проверю. У меня, скорее всего, оно опять включилось.
Давайте опять залогиниться.
Giovanna.
Thank you. So, good morning everybody. Let's begin today's lecture. And we are starting from the analysis of yesterday's problem. Well, actually the day before yesterday problem. So let's begin with problem A. And statement for problem A declared that we had some arrays with numbers, and numbers were only from 1 to 1000, and we needed to choose some numbers in each array. And we needed to do it the way that total sum of all the numbers was maximized, and there were no more than k numbers chosen in each array. And all numbers should be distinct, pairwise distinct. Several clues in this problem showed that it's a problem for using flow algorithms. First of all, we have like not very large values of all the constraints. Like we have only 50 numbers in each array, only 50 arrays. We need to choose only no more than 50 numbers. All numbers are from 1 to 1000. This kind of looks like flow problem. And the second clue is that we need to use any value from 1 to 1000 only one time, and we need to use every array, no more than k times. These constraints usually like show that the problem should be solved with flow algorithms. So who can answer how to build a graph? in this problem? Yes.
Make a node for each array, and it points to all the numbers it has.
Okay, so we have, yeah, actually I'm going to draw the graph I have on the next slide. So I'll just switch. Yeah, actually we need to build a network which will have two layers, and first layer will be responsible for our arrays, and second level will be responsible for our possible number values. So we'll have around 50 nodes in first level and exactly 1,000 nodes in second level, and from the source we'll draw an edge from the source to every array, and the capacity of this edge should be k, because we can use no more than k numbers from every array. Then for every for every occurrence of some number in some array, we draw an edge between this array and this number, and capacity of these edges should be 1, because, well, we can only use once every occurrence of some number in some array. And finally we draw some edges between numbers and finish, and vertex t, and capacity of these edges should be 1, because we can use only once every possible value of our numbers, and price should be 1000 minus 6. It's only like one of the possible like solutions, I guess. So this way, when we when we are trying to add some additional unit of flow flowing through the graph, we'll choose a path which will contain the cheapest edge, so it will contain the maximum possible number. So after that, we have this graph, and we calculate maximum flow of minimal cost, and it will be our answer. So that is one of the possible solutions. If you know how to write maximum flow of minimal cost, you probably will easily do it in this problem. Another solution was not to use a flow algorithm, use a maximal matching algorithm. We could build a graph with n times k vertices in the left side and 1000 vertices in the right side. So first k vertices in the left side are responsible for the first array, second k vertices are responsible for the second array, and that goes on. And then we should draw an edge between all vertices responsible for some array and the number that occurs in that array. For every occurrence, we should draw k edges. So this way the graph will be bigger, but it will still have at least, at most, 2.5 times 10 in 6th degree edges. And so, yeah, no, it probably won't work. I was going to say that we can use maximal matching algorithm after that, like add some number and trying to find additional paths for our new number, but still it will be too long for us. Okay, so the solution with maximum flow still works. This is good. Let's proceed to the next problem. And the next problem was called Gundex. And the statement you can see on the screen, we had some set of strings, and we needed to do some operations on it, like adding the string, increasing rank of the string, and getting the string with some prefix and the hash string. So the only natural data structure which comes to mind in this problem is tree. Let me switch to the next slide. And we need to store some additional information in every vertex of our tree. And this additional information should be maximum value of rank in subtree of this vertex. So after that, we'll have our query operation. Well, actually, we need to store not only the maximum value in subtree, but we need to store the link with the leaf with maximum value of the rank. So this way, our query operation will work in constant time because while we stay in any vertex, we can just see where our link goes and take this vertex as our answer for a query. And any update operation will take linear time of the size of the string we are doing this operation for. And but so it's absolutely okay because well we still have to read all strings with which we'll be doing some. We still need to ring all the strings with which we will do some operations. So linear time in this case is okay. Anybody have questions about tree? I guess it's pretty common data structure. So the next problem was geometry problem. We actually were surprised that like a lot of teams solved it only on the last hour and nobody tried to solve it before. So at some point standings of the contest looked like this. There were like 8 problems which should be solved by strong teams, and all the strong teams had 6 problems because 2 other problems was geometry. So we were a little confused about that. Why don't you like geometry problems? Why don't you solve it? Why are you laughing about it? Okay, nobody answers. So in that problem we had a convex polygon in the circle, and we simply needed to find their intersection and find the area of this intersection. So actually we needed to, there were several solutions for this problem. One of them was just to like calculate the area, split the area of the intersection into 2 parts. First of the parts would be just convex polygon, and second of the parts will be some circular segment. To do it, we only needed to find 2 intersection points. We could do it by going around the polygon. Oh, actually, this polygon is not convex. That's interesting, but doesn't matter. All we needed to do here was go through all the edges of our polygon, find intersection of this edge with find intersection of this edge with our circle if it existed. So after that, we'll have 2 points, and these 2 points can help us to complete the polygon and can help us find the circular segment. And after that, we should calculate the area of polygon and the area of segment, and that will be our answer.
Well, I was trying to do it that way, but there are other cases where there are more than 2 intersections. It could be like 4 or 6 or 8. So I didn't know how to fix that.
Oh. Okay, then you can calculate all the intersections and then take all the points which lie inside the circle and find their convex hull, I guess. It's becoming a little harder than I thought, yeah. Okay, so if you have a circle and you have some polygon, So what we have initially are these vertices. What you will have after you find all the intersections will be these vertices. And it's possible there that it will be some vertices. It's possible that it will be some initial vertices as well inside the circle, but it's okay, I guess. So after that, you can find the convex hull. We'll go like this. And after that, you can check if and after that you can check if some edge is part of the original edge, then you don't need to add this sector of the circle. And if some edge of convex hull isn't part of the original edge, like this one, for example, you need to add this area to the intersection, and this area is also a circular segment. So the answer will be area of the polygon plus area of all the circle segments you need to add. I guess that will work. So yeah, the analysis of this problem was probably not good enough on slides, but this thing will work, I'm pretty sure. And also, Artyom told that you can solve this problem with integration. Like it won't be precise solution, but it will still work, since precision we needed here was only like 10 in minus third degree. So you could do some non-precise solution, and it will still work. So any questions about this problem? Okay. So yeah, actually it's harder than I thought. You need to know an algorithm of convex hull here, but I guess you know it. Maybe you discussed it with Gleb when he discussed geometry. So let's proceed to the next problem. The next problem was called LCA, yet another LCA problem. And what we had there was a tree, and we needed to find all the vertices which have maximum amount of pairs of their predecessors. So for every vertex, we needed to find amount of pairs of the first phrase, the first description of the problem wasn't correct. So for every vertex, we need to find amount of pair of vertices for which this vertex is an LCA. It's actually written on the screen. Let's proceed. So we need to find two values for every vertex in this problem. First of the values is size of subtree, and the second, well, actually we need to find one value. It's only the size of subtree, and then we can calculate answer for our problem, like during like just take all the vertices, and for every vertex we can calculate an answer. How are we doing it? If we have the size of subtree for every vertex and we had a set of children for every vertex, we can just take all pairs from our set of children and calculate multiplication of their sizes of subtree. Well, actually, we can't do it like write 2 4 cycles and take all the pairs, because probably we'll have graph something like this. Yeah, and we'll have n edges going out from root. So this thing will work in n squared time, and it's not what we want here. But if we can calculate the number we need in linear size. So I guess that was the only challenge in this problem. Do I need to explain how it's done? How to find the number we need in linear time. Well, nobody needs it. Let's go on. Yeah, I would be surprised if someone needed it. So, next problem was problem about ASCII graphics. We had a picture of tree written with some symbols, like O, large letter O was the vertex. We had edges drawn with minuses and pluses. And oh, yeah, okay. Well, that's actually even better. Okay, so, and what we needed to do, we knew that this was a drawing of some tree, and we needed to find this tree. So actually, the solution was, the solution wasn't that hard. We needed just to give numbers to all occurrences of our large letter O, capital letter O, because every occurrence is a vertex. And then for every occurrence, we need to do the following things. We need to, I thought somebody was going to ask something. We need to find all the edges going out of this vertex, and just go along these edges and find the vertex and that is lying on the other end of the edge, and add a pair of our vertices to an answer. So after that, we could get some tree, and this tree was an answer. So the next problem was another geometry problem, which was maybe harder because it was about three-dimensional geometry, but still it was it had some solution you can write in some time. So what we had a sphere and a point with array. Actually, a point with array, I guess it doesn't matter then it's a point and array. It matters only that we had some line that didn't touch or intersect a sphere, and we needed to find some plane which contains the line, and we need to find some plane which contains the line and only touches the sphere. So I was trying to draw some 3D pictures for this problem. I haven't succeeded. So for this problem, I will draw pictures on a board. So we have some sphere, and we have some line that doesn't intersect it, and we have some point on this line. So let's for the first thing to do in this problem, let's project something on. Let's project everything on some plane to get a two-dimensional picture to understand what's going on. So what we have here, first plane we can use is the plane which actually contains the sphere center and our point and our array. So this plane would look like this triangle will be in this plane. We can take this plane and we can actually get the equation of this plane from any 3 points. We can take this center of the sphere, and we can take the point our array goes out from, and we can take the vector of our plane, of our array. So the next thing we can do, we can find on this line the closest point to the center of the sphere. It will look like that. And then we can draw a plane which goes through these 2 points and is perpendicular to our array. So actually we already have a normal vector for this plane, and we have a point for this plane, so we can just build it. And this plane will, I'll try to draw it, and this plane will cut our this plane will cut our sphere. somehow this way. So after that we can get a projection of every item we have on the second plane, and we'll have a picture like this. So the point is, which marked as ray is actually this point. It's the point closest to our sphere on our line which contains our ray. The line marked as plane is actually the first plane. This is the red one which contains the ray. And the ray is actually perpendicular to a plane we were projecting everything on. So now the rotation of the plane around this ray will look just like a rotation of the line we have here, and which is marked as plane. So after that, we only need to get to find one angle, and this angle is angle between the projection of our plane and the tangent line for our circle. Well, it's obviously that sphere is projected to the circle. So we find this angle, then we rotate the plane on this angle, and then we get an answer. We get actually a plane which we get the plane which touches the circle but doesn't intersect it, and, which touches the circle and contains the ray. Well, actually, we even didn't need to do some rotation operations. We could find just we could find the vector. Yeah, we actually could find the vector of normal vector of our tangent line, and we could use it as the first vector, and we could use ray as a second vector, and we could get a plane from these two vectors. So we even didn't need the rotations here. We only needed some basic 3D operations with planes, vectors, and stuff. So, any questions? Are you going to? No? Okay. Oh.
Is your cell phone?
Yes, it is. I'm sorry. Okay. So, let's proceed to the next problem. And the next problem was poker. Does anybody solve it during the contest? Or after the contest? So nobody. Okay. Well, actually, the poker is, I guess this problem is a good training for writing some like very complicated, well, not very complicated, but very long code with a lot of like constraints you need to check, and the code in which you can do like any typo, and if you will do it, you will look for it for the rest of your life. So I guess this is a good training to write this problem. I actually didn't solve it, but I tried to write some other poker problem. I don't remember if I succeeded. It was a couple of years later in the same Peter Zavod's camp. So what we had there was poker game. We knew everything about this game. We knew hands. We knew all the cards which will go on the table, and we needed to calculate some probabilities of winning for each player to win. So the idea of solution of this problem is actually obvious. You just needed to like brute force all possible combinations and find who is winning in every combination. But the only problem was you have for the first time when you don't know when you don't see flop and turn, when you don't see any cards which will go on the table, you know only hands. You have a lot of possibilities, and if you will check the combinations, like just check it somehow, you probably will fail the time limit. So you needed some optimizations. Well, the example of optimization you'll need is checking for straight. A straight is, as you probably know, 5 consequent cards like 5, 6, 7, 8, 10, or well, that's enough. And so what we needed to do here, what we could do here was when you are checking for straight, you don't need suits because it's only about the values of the cards. So what you could do, you could ignore suits and calculate some masks and some possible masks of the of all the cards. We'll have like 52. No. We'll actually have like 13 in 7th degree possible masks. It will be around 10 in 7th degree. So you can calculate the set of masks for which you actually have straight and store them somewhere. And when you need to check, you can just only get the mask from the set of cards and get the mask for set of tasks for set of cards and check if this mask have straight. So any other examples? I guess you actually can do this optimization with some different combinations also. So you definitely can check for square, for example. Oh, for how is it called in English? For four similar cards. So with some optimizations, the problem will work. And I don't know if you have any questions about it. I'm going to try and answer them. So otherwise, we can proceed to problem H. So the problem H was about some data structures. It had some cubes, some set of cubes, and you had two types of queries. Get the number of colors on the upper side and reverse or rotate some segment in the reverse and rotate some segment in the our structure. So well, actually this problem was about data structures. So when you see the operations like take a subsegment of array and do something with it, like reverse it or do something, it's probably will be the problem about data structures like Cartesian tree. So we're gonna store all the cubes in Cartesian tree and in implied Cartesian tree, and for every vertex in this tree, we're gonna store a table 6 by 6, and we're gonna store the amount of each color on each side of the cube, on each side of the on the segment of our tree. So after that, our queries will be expressed like either applying some permutation to all the arrays or reversing and possibly reversing the subsegment. So yeah, that's the next slide. So if we are rotating our cube without reversing it, then we can just apply the permutation. In problem terms, it will look like we have a cube and we are rotating it like in this direction. So we can just like change places, change some arrays with each other, and it will work. And otherwise, we are reversing it, so it will still work. So the only thing we need here is like subsegment operations on our array, and it can be achieved with Cartesian tree with flag and permutation. And the important thing here is that applying permutation is actually additive operation. So if you know that you should apply some permutation p to our vertex, and then you know that you should apply some permutation s to our vertex, you can actually multiply these permutations, and it will work. So you don't need to push the first permutation to the children just to apply the second permutation. And it's actually a good thing, because without it, the segment operations don't work. Okay, so the next problem was called union. And in this problem was again about LCA. And in this problem, you need to answer some kind of queries and the query was get the number of edges on the path from one vertex to another that have a weight less or equal than k. So first step will be dividing our queries in 3 different queries. If we have root, we have some subtree of it, and in subtree we have vertex U and vertex V, and we have an LCA of these vertices. What we could do here was say that the result of our query will be this length plus this length minus twice this length. It's actually what's written on the screen, I guess. And so for one query we get 4, but this 4 has good condition that they all are a query from root to some other vertex. So after that, oh yeah, it's actually the last slide of this problem. So after that, what we need to do is go with depth first search, walk along our tree, and for every vertex we can calculate. And for every vertex we need to add all queries at once. Yeah, for every vertex we need to answer all queries at once. So we go from root to our vertex, and we add edges on the way, and we have some structure that answers some queries about amount of numbers less than k, and that's basically it. So we come to the vertex, we answer all queries, and then we add another edge and go to some child of our vertex. And so we need some data structure. It should support operations insert, delete, and get the number of numbers less than k. And you can use actually a lot of different structures. You can use segment tree, Fenwick tree, Cartesian tree, any other binary searching tree, binary search tree. Yeah. So I guess that's pretty clear. So the next problem was called what? It was the last problem of the contest, and there you had some enemy, you were fighting it, you had some hit points, enemy had some hit points also, and you needed to choose a weapon, place to shoot, and shoot the enemy several times, and you had some probability that you're gonna hit him, and you needed to calculate the probability of you will kill him, of you killing him. So the constraint we had in this problem was that our hit point amounts were pretty small, so we could use dynamic programming, and the states of this the states of this dynamic programming will be will depend on two parameters. One of the parameters will be amount of hit points the player still has, and another one will be amount of hit points that enemy still has. So after that, we can pre-calculate for every pair of weapon and for every pair of weapon and place to shoot, we can pre-calculate the probability to hit exactly k times, and after that we can just iterate over all these pairs and choose the one that is the best and like apply it to our current state. So we have like big complexity in terms of problem in terms of values, like amount of hit points on player and the enemy will have like complexity you see on the screen, but these values were pretty small, so it probably will work if you do it right. So I guess that's it for today's analysis, and if you have any questions about problems, we can discuss it now. Yes?
How can we use dynamic programming? Because if I remember correctly, you could miss all the shots, so you could go from the same state to the same one.
You need to divide. If you have priority 0.2 of go to the same state, divide for 1 minus 0.2 and have the priority.
Okay. So you're satisfied. Okay. So if you have any questions about the problems, if any other questions about the problems, okay then. So I guess, yeah, we used a minimal flow of maximal cost, maximum flow of minimal cost. Do I need to explain this thing? We're still talking about the problems. No, don't need it. Okay then, let's do an intermission now, and after that we'll have a lecture. Разборы ускоряются день ото дня. Где? Ну, кстати, да, на первых разборах мы использовали какие-то вообще сложные вещи, я даже что-то рассказывал. Какие-то алгоритмы.
Teste som, teste canal B. Alô, som. Troca de microfone. Só piora. Voltando pro microfone antigo. Ele ficou melhor quando voltou pro antigo. Então deve ter a ver com o microfone, não? Pode ser, pode ser. Tá.
Sound testing 1, 2, 3. Som. Wilson. Can you hear me, Giovanna? Please talk to me, G.
Fica fácil fazer, né? Eu também sinto a mesma coisa. Eu acho que, nossa, um bom esse produto.
Really? How is the problem?
Porque, tipo, olha, você não vai pra gente. Eu não seguro que você não
How is Okay.
É sempre errado.
Well, it's actually, if you see one vertex inside the circle, you say that was one.
Que legal!
Well, yeah, that's probably wrong.
Pessoas mais novas fazem se influenciar, né?
Yeah, until we get that out.
Não, aqui pra você não.
Yeah, this one. Yeah, actually, it's the pairs of So yeah, it should work. Well, just have some bug. But yes, it should work. If you calculate the area of this, if you calculate area of these sectors correctly, then I don't see.
Mentira, não dá pra não, mentira. Isso pode fazer.
Well, it's actually like a lot of cases you check. You probably just have some bug.
I also get to see that the same
E daí podia tudo. Assim, claramente. Maior Miguel. Eu vou guardar essa data. Nesse vai dar certo. Porque nesse só sai
But in this case, if the center of the circle is inside the polygon, it will still be Oh, well, so you're designing based on if you do not have sections on some of angles, if the center is inside the polygon, it's like a lot of cases. Something why won't work in this So I guess even in this case, and we just check for an edge if it's part of like original edge. This is not the edge. This is not the edge circular segment. This is not the edge circular segment. So this problem. And actually, I'm not sure how it works in the case when the circle is inside the wall. Then have no intersections. No, just wait, I'm trying to play this solution in this case. We have no intersections, so... I'm trying to avoid like sophisticated checks for another cases. Because yes, we can, if we have no intersections, we can check if the circle license has a polygon, the polygon license has a circle, if they are like separate. But that's not
Começa com Zé e termina com 3.
I guess there is a system of some text. Yes, text.
Como é que os caras estão lá fora
I guess I
calor
would
de
find like
fritar na Europa?
problems with text geometry. I guess you find some geometry problems.
I think it should be easier, and like when you have a problem that requires you to have not too much precision. So, for example, here you have just like 1/1000, yes. So it's just like natural to find some approximate solution, not this kind of exact one.
Makes sense.
Все? Пришли в читать?
Thanks.
I have no cell phone with me. Yeah. Okay. So for today's lecture, I'll start with the finishing last lecture. So we finished talking about heavy light decomposition, and I plan to do some more about the queries on trees. So we'll first do that and then move on to next topic. So heavy light decomposition, then we'll talk about centroid decomposition. This was one of the points in questionnaire that Glad sent you before, and it was surprisingly low. So not heavy light decomposition, but centroid. So, first, what is centroid? Anybody here knows what centroid is? Okay, so let's have some kind of tree. So let this tree have, suppose this tree has n vertices, and the centroid is a vertex S, let's say, that if we make this the root, then all of these subtrees size strictly less than n over 2. So the centroid is the vertex that, if we remove this vertex from our tree, all the remaining parts will have size less than n over 2. So the S is centroid. Okay, the first natural question: does centroid always exist in a tree, and how to find it? So yes, it does always exist, and right now we'll write an algorithm for finding the centroid of the tree, so that, and it will also be a constructive proof that it always exists. So suppose we have this tree again. Let's draw it from this. Let this be the root for now. Okay, so this is the same tree here. So let's make our tree root. For example, if n equals 2, there is no, but there always is if we have less than or equal. Okay, so now after we've calculated the sizes of subtrees, then we just go from root and see. Is this the centroid? No, because it has a child which has size more than n over 2. Then we go to this check. Is this the? It has two children. One has size less than n over 2 and one has size more than n over 2. So we go there. Is this the centroid? Well, it has children 3 and 1, which are both less than n over 2, and it has something at the top. But can this something at the top be greater than n over 2? Well, let's consider the last moment here. So we have, so first we were at the vertex. This size is greater than n over 2. Otherwise we wouldn't make this step. So this means that the remaining of the tree has size less than n over 2. And this all has size less than n over 2. So after we make this step, after all children of the node have size less than n over 2, then everything above that vertex is also less than n over 2, because this was children with size more than n over 2. So we just go, so the algorithm is as follows. We just calculate all the sizes. We just go from root to next vertex, while the size of that vertex is greater than n over 2. And after that's done, we'll have this vertex as a center. So this is both the algorithm and the proof that the centroid always exists. And this will be our base for this. So, the centroid. Suppose we have this tree thing. And we find the centroid. And let's remove it from this tree. We have now 3 trees. Each one has size less than n over 2. So let's find the centroid here again. And remove this one here, remove this one here, remove this one. And we'll have 4 trees of size 1. And then we remove them. Let's say that the time at which vertex u was deleted, we'll call where u is the time when u was deleted. So it was the So some observations about this one. So the first, the max layer is no more than log n. Why is that? Well, because each time the size of the tree reduces by at least twice. So we'll have so after log n steps, we'll have all of our reducibility. Okay. So suppose so let's have the vertices UV with the same layer. Then there is some vertex S with the layer lower than that. So that the path from U to V goes through this. So let's take an example here. We'll have these three vertices have layer 2. So all of these paths go through the vertex center, which has layer 0, and all the paths between the other vertices also pass through the vertex with layer 1 or layer 0. Okay, so this will help. So these are properties of that they just help you to solve problems using central decomposition, and you don't need to know them to outside central decomposition. Great. So what do we do with that? So let's create this array. So let's, for each vertex, let's list all the roots. Let's list all the centers with the same tree as U up to the point where it was deleted.
So U will be blocked with this list, and he will have a 0, S1, SK, SU, and U. So this was the center of the tree. This was the center of the tree after the first center was deleted, and it was
the same connected component with U. So this is just the list of centers which were in the same connected component as U, while we were in our processing of building vertices. Let's do the same. They might not have the same length. So these two are obviously equal, because they are in the same tree before all these operations. So let's find the longest common prefix of these two sequences. Okay, let's say it's somewhere here. So this was the last root. Yes. I guess. This was the last root of the tree where after deleting this root, these two vertices became this kind. So you already know how to construct the centroid decomposition. So while you have vertices still in tree, find the root of each tree, remove it. Find the centroid of each tree and remove it. And so I think it would be better to go with an example of problem which uses this kind of decomposition. So suppose we have a tree. And as always, some queries to it. So the first query would be color all the vertices. Vertices U with the color C, such that the distance from U to some vertex I is not greater than I. This problem was proposed in last Open Cup Grand Prix of Kazakhstan, I guess, and one of the teams here solved it. Well, we'll solve it as well. We want to color all the vertices on the distance not bigger than some same distance. So if we want to color all these vertices here on a distance not bigger than 1, then we'll color these four vertices and this one will be still. We'll still have the initial color and get the color of the vertex. This is the problem that I think is not approachable by any standard decompositions, and it is pretty easy using the centroid. So, okay, so let's for each vertex it gets deleted at some point. So for each vertex, we'll store the list of queries. So we'll have there was a query di with the color ci, say d1 c1, d2 c2, and so on. And by the way, this can be done online using the central decomposition. So, what do we do when you have the query of the first type? When there's a query of the first type, you have the vertex U and some root as I. So remember this list we'll just run over all vertices of this list. So there is the path from U to Si. Let's say it has length L. Then let's color all the vertices from Si on distance, which have distance to Si not greater than Vi minus L. So if we have the query color all vertices that are from distance no longer than di from U, then we transform it to log n queries to these roots. So instead of coloring all the vertices which are in distance no greater than x, we'll color all the subtrees of some particular root. So when Si was the center of the centroid of its tree, we save this tree and we make the Si the root of that tree. So after that, we just have to color all its children that are on distance no longer than Vi minus L. So it's some kind of top of the tree. And we do that for all Si. And when we have the query of the second type, we again go to all the roots, Si, and see which queries of the first type were added to this project. So we just look over these pairs, take the one with the largest D, and look if it reaches our vertex. If L is not greater than Vi, then it has the color Vi. And if it's not, then we just move to the next. From all of these, the I's, we choose the latest one. So it might not be too understandable, but that's what I wanted you to get, that we can transform the queries of type do something to all vertices on some less than some specific distance, to all the queries on the subtrees, and this is the only approach I know with this kind of. Okay. Do you have any questions about this one? So now to easier topics, I guess. So what I wanted to tell you about today is the matchings and flows, graphs. So let's start with matching and then go to flows, and we'll see how these two problems are. So the matching. So flows will have a department graph and some matches. we want to. So what is matching? Matching M with the subset of edges of this graph, and for all two edges in this matching, we have no two start points or no two endpoints correspond. So let's say beginning of the one is not the same as beginning P2 and the same thing. The problem is to find the matching of the maximum size. So we want to maximize the size of this. I'll just go through it quickly because most of you already know. What is this about? So so suppose we are adding our vertices to the left part one by one. So we have this one, this one, this one, and so the algorithm for finding the maximum matching is as follows. Go through the vertices of the left part and run the diagrams. So we run the DFS of U, and we see we run through all its neighbors in the right part and consider two cases. If there is no match for V in what we've gathered so far, so if there is no match for V, we just match U to V, and that's all. So for each vertex in the right part, we'll store the corresponding vertex in the left part. So here, after first iteration, we'll have two neighbors of the vertex U. And it so happened that this was the first one, and we'll just point this here. And we'll say that this edge is now null, and this is in our matching. This will also return true if we found any match, and false if we haven't. Here we go. Great. And if it's not, if there is some match. So suppose on the second iteration, when we go from this vertex to here, we look at this edge. This vertex is already taken, but we can try to run the difference from here again and see if we can find any other match for this vertex. So it's a DFS, so we don't want to visit any of the vertex of the left part twice. So we have some, as usually have some array tracking which vertices we visited so far. And we just mark it as true and we enter this. Else, if we haven't visited the match for this vertex before, so else, if we haven't seen vertex V, the vertex match V, we can try to find the match from here. So if we found that, then actually we've already went through some kind of chain, and this vertex has been matched to the other vertex. So when we start from this, we go here. We say that its match is not now. So we go here. It's not visited, so we go here. We look through all neighbors. This one is taken, and this one is not taken. So we now say that this edge is bound, and we point from here to here. And after we return from that procedure, we say that this edge is bound. And we point from here. So what we actually do is we find a so-called alternative path. So we have some vertices here, we have some bold edges here. And it's called kind of edges. And what we want to do is to have thin edges point to the right part. Both edges we want to point to the left part. So we make our graph directed instead. Do you understand what happens here? Any questions so far? So the edges that are already in our current matching point to the left, and all the other edges point to the right. And so we want to find an alternative path, so that from this vertex to any other vertex in the right part. Here. So here we have here, and here. And after that, we change all the edges on this path. So this path will always look like thin edge, bold edge. Thin edge, bold edge, and thin edge. So the edges on this path are alternating because our graph is tripartite and the thin edges only point to the right and both edges only point to the left. So, and then after that we change all these edges on this path. So we'll have this path becomes bold edge, thin edge, bold edge. Bold again. So we see that here we increase the size of matching by 1. So here we have 2 bold edges that are in our matching, and here we have 3 bold edges. So this one is basically describing this process. So we go through all the thin edges from the left part. If we found the end of our path, we just flip this edge. And if we haven't, we try to go from the bold edge that comes from the end point of our current edge. If we found the path, we just do the same. And if we haven't found anything, we just return. So this is one DFS, and just to make our algorithm complete, this is the algorithm. So for all you in like left part of our graph. We just clear the distributor rate, just like before we do before any DFS. And we just run the DFS from here. So this is the whole algorithm. We'll go for all vertices in the left part. We run the DFS to find the alternate path, and we just, if we find it, then we increase the size of our region by 1, and if we haven't, then this vertex can be here. Good. So this algorithm works in. We run the DFS n times, so it's n multiplied by n. And it's called Kunz algorithm. It's Hungarian mathematician. And it's really fast in practice. And there are a lot of optimizations that can make it even faster. So an example of an optimization would be to not run through all left vertices of left part, but shuffle it before. So we shuffle the left part and we run the inference from vertices in random order. We can do it the same with. We can do it the same with order of edges here. And there's one more optimization that we don't run this else. Instead, we run 2 fors. So the first for will just search for the available vertex. And the second for, so the first for will just have the condition that first for will have the condition that there is no match, and the second for will actually recurse. This helps us to avoid this kind of situations. So we have this kind of graph. And this vertex points to this one, to all before, this one to all before. So what our basic algorithm will try to do is to match this one with this one. It's okay. Try to match this one with this one. Recurse here, don't find anything. Match with this one. This one will try to recurse here, then match with this one. And if there is always a match, you can see the matching, the perfect match is trivial. And so we can find our matching faster in this kind of graphs. It doesn't always help, so sometimes we just do some unnecessary work running twice, but I guess it more often helps than it doesn't. So So we'll start talking about flows, and we'll later see how this is connected to this problem. So the flow problem is more general, and you can solve maximum matching with flows. So this is like the classic example in network flows. So you would have a graph with 2 vertices separated from all that. So the first one is called the source, and the last one is called sink. And so we have this graph, and all the edges have their capacity. It's some positive integer. So what we have is 2, 3, 1. we'll see how this works out. So the flow is the function. So flow UV is the amount of flow of some, I guess you can imagine it is as like liquid pouring from vertex U to vertex V by some cubes. So this is some function from edges of the graph to all integers, not necessarily positive. So if I'll introduce the definitions for that. So first, the amount of liquid pouring from U to V is the same as the amount of liquid from V to U plus minus. So we can have negative flows. First, for all vertices that is not sink or source. The sum over all edges should be 0. So for all vertices from S to T, the amount of liquid pouring into this vertex should be amount of liquid going out of this vertex. And it shouldn't be greater than the capacity of the edge. Not be greater than capacity of the edge. So only 3 units of liquid can go through this edge, and only 1 can go through this edge. So for those familiar, it's not necessarily integers, but it will be integers in all our problems, but it's not necessarily. So it can be anyway. So in this, so for those who are familiar with linear programming, this is the linear program. So we have the restrictions of less than or equal, of an equal type, and we want to maximize sum of all flows going from the source. So we want to maximize that. And as you can see, this is the linear program, and it can be solved with linear programming, but there are more efficient algorithms for this. Okay, so let's try to increase our flow by at least 1. So we have this network. And we just run dfs. From S, T, and we go over edge where we can only find where the remaining capacity is not 0. So suppose we go this edge. So suppose we go this edge, then this edge, then this edge. So we found the path, and we can just increase all the flows on this path by 1, and you can see, you can prove for yourself that all the flows, all the flow properties are still correct. So after that we can find another path. So we can even add 3 on this path. And there is still one more path. It's like this. And we add the 1. So all the edges are separated, and this is indeed the nice one. But this could be important that we sometimes cancel the flow from the existing edges. So, for example, we modify this. So I guess this network works. So suppose we have found this one as our first path. We have 2, 2, and 3. After that, there is no more path from S to T if we just say this is 0, this is 0 instead of 2, this is 0, and this is 1. I guess there is one path. Let's make this also 1. So if we found this path and we just set all the capacities to 0, since we have 2 units of flow through this path already, then we actually can't find any more path, because like, this path is blocked, this path is blocked. So sometimes we need to cancel out edges in the flow we have already found. And the way we do this is will allow us to traverse the edges in their own order. So the solution in this case will be simple. If we have the capacity, if we have some edge with some capacity from U to V, we'll add the same edge, we'll add the reverse edge from V to U with the capacity of 0. So this will allow us, because of this property of flow here, so the flow is asymmetric. When we add 2 units of flow here, we actually subtract 2 units of flow here. -2 out of 0. So whenever you see the negative amount of flow, you know that there is actually flow in the opposite direction, and we can cancel this flow. So it's the same as having some flow in the opposite direction from B to E. So the basic algorithm for finding the flow will be as follows. So we find flow. So we want to find an alternative path. Not alternative, but we want to find the path. So we want to find paths S0, S1, K, where S0 is S and Sk is T. And we want to modify the flow. So we have Si plus 1. We add 1 to it, and to have the properties of flow remain intact, we need to subtract the flow in the opposite direction. So, and while we find this path, just find path and increase the flow. We can always see that our objective function increases. So if all capacities are integers, this will eventually terminate, and this works in m multiplied by f. Of course, here you can add not just one, but the minimum remaining capacity on this path. But let's do it like this for now. So this is m multiplied by f max. This can be huge if your capacities are around 10 to the 9s. So don't use it. But if you have small capacities and not too much edges, you can just run the simplest algorithm and find the maximum flow. So in relation to our previous, we'll construct the reduction from matching problem to flow problem. So here we have our initial graph without these two vertices. We'll just have all the edges directed from left to right, and we'll add the artificial source and artificial sink, and have all our capacities set to 1. 1, 1, 1, 2, 1, 1, 1. This means that when we find some path, each vertex on the left can be used more than once because we have the capacity of 1 here, or 1 here, and we have the capacity of 1 here. And the Kunz algorithm actually works exactly like this. So whenever we find the path, we reverse the edge. It's the same as adding one flow here. So removing the direct edge and subtracting the flow in another direction, thus creating the reverse edge. So this would be the same as finding flow from any vertex, finding the path from this vertex to here, here. So we find this vertex, we change this edge's direction as this, and it just works. So this is a bit more general algorithm for the same problem. Kunz algorithm is still useful because it's easier to code and you can add optimizations to it. It's harder to add optimization to the basic flow algorithm. So this point here is kind of ambiguous one. So there are several ways to find a path. So this if we use US, and you can create a graph where this is the bound. But if we use BFS. Find the path here. Complexity becomes n divided by square. So this is already polynomial. So if you have not too many edges and vertices but still big capacities, you can use BFS instead of DFS. And this will, let's say, this whole thing will work in n multiplied by m squared. I won't prove it here. It's somewhat difficult to prove. Just know it. So this bound is still holding with BFS. So whenever you can, just use BFS. So that's it for the basic flow. We'll then move to the more complicated concepts and its relation to other complicated concepts. So first, suppose we have some graph G, and we already have some flow in it. So there is FTV. There are capacities. We can also think that the capacity function is defined not just on edges, but on every pair of vertices, and just say that it is zero that where there is no edge. So we can think it is either from E2 integers or from each pair of them. Okay, so suppose we have some flow already. Let's consider the function C U prime V as the difference between capacity and the existing flow. So even if this is zero, this can be greater than zero because remember that flow can be negative. So we have our graph U prime with the function C prime, the new capacity function. This one is called the residual network. This one is called the residual network, and the old algorithm actually finds any path in the residual network, then modifies the residual network. So when there is no path in the residual network, the flow is negative. So this is like the classic example. Most of the computer science books that talk about network flows use this example. Get used to it. So, for example, if we had all the capacities to 1, and we found 1 unit of flow along this path, the residual network will look like this. So there's no edge from this here. Still 1 unit of flow here. 1. there is actually 1 unit of flow in this direction. This direction. This direction. And the 2 edges pass to this. So this is the residual network for this path. So for this graph, and we see that there is still a path here. It's just an illustration that the adding of the reverse edges is important. The algorithm doesn't work without the loop. But there is still application for this kind of edges. So let's talk about walking flow. So the walking flow is a flow function that for every path from S to T, you can push some flow in this path. So, for example, this flow here is blocking because every path in the original graph, not in the residual network, contains at least one edge that is full. So you can push any flow using only edges from the original graph. This is what's called blocking flow. Then we continue with what's called Binet's algorithm. This is like in my opinion, it's the easiest flow algorithm that is suitable for contests, and it's fairly fast, and it even has like theorems about how it works on graphs with unit capacities or with small capacities. Oh, we'll talk about that. Okay, so this algorithm is like this. So while we do the following thing. Let's consider the residual network, so G prime, and let's find the distance in edges, so run DFS. S from the source, and we find all the distances from S to. So for all vertex U, find the shortest distance from S to U. Then we construct the next graph. Here it's important to note that we run this in residual network. we run BFS in residual network from the source, and we find all the distances from starting node. Then we construct another graph, which contains the same edges, the same set of vertices, but the edges here are only edges from U to V. That the capacity is greater than 0. And so remember when you run BFS, it splits all your nodes into levels. So we have all these layers with distance equals 1. This is the one node with distance equals 0. Here 2. And eventually we come to there. So here we construct the network, which only has edges between adjacent levels. So we only leave this edge here. This edge will not be there, and this kind of edge will not be there. And there can be no edge from here from two levels ahead. And why is that so?
If there was, the node would be on that one level before.
Yes, so the distance here is 1, and the distance here is 3, and there is a path of length 2 here. And the distance array is not correct. So we have distance here, and we have distance of endpoint equals the distance of beginning plus 1. So we construct a new graph. So it's basically the same edges, but we remove all the ones that don't just are not between the adjacent levels. So here we find any block and flow. And repeat. So we find block and flow in this new graph and just add it to the existing flow. Let's say it's F prime and J, and then just say F3V add prime. So this is the abstract Venus algorithm, because there is still a point where we can implement different algorithms. So at this point we can plug any algorithm of finding block and flow we know, and we'll get a different algorithm. But let's discuss how to find any block and flow. So, in this kind of network, finding block and flow is actually really easy, because consider any network. So this works equal to the level 1. And this is 3. level 1 and this is level 2. It's somewhat trivial, but so the only interesting edge here will be this one. So the first residual network will look like this. We have these edges. And we have these three vertices. This one is T, and there is only this edge. So this is our constructed network, and the only path we are interested in is this one. Because it's the only path of length 2, and there are no other paths. So we have this flow here. And basically, instead of these two edges, we add the reverse. So after that, the residual network will be more. We still have these two vertices. This one won't be on level 1 because there is no path of length 1. So this would be our network. There would be an edge from T to this vertex. But we don't care since we only want to go from S to T and we don't go anywhere further. So notice that the distance from S to T in our residual network has increased. So here it was distance equal 1 to 2, and here it was 3. That's not a coincidence, and actually, when each time we run BFS here, the property is that distance ST increases. So with this each iteration, the distance increases. That means the distance can be greater than n-1. That means that there is only linear number of iterations. So linear number of iterations, and where there is no path in the residual network, we are sure that there are no paths that can be added to our flow, so our flow is maximum. So linear number of iterations will then find working flow in M. So the whole algorithm will be all n squared M. The old algorithm would be BFS as m squared, and m is usually greater than n. So the number of edges is greater than the number of vertices. So this is usually faster and pretty much faster all the time. So here we find any blocking flow, which is like this one, this one. And this is the maximum flow because there are only 3 edges from the source, and we found the flow of size. So this was somewhat a trivial example, but it illustrated what I wanted to show, that short distance always increases. It, of course, can be proven, but I won't. Okay. So the blocking flow. We'll find the blocking flow using DFS from .cu. And we also store the current flow. So in DFS, we've traveled through some path here. And we've come to the vertex U from S. And there is some kind of minimal edge on its path. It's called M. And we'll also store M. So the M is the amount of flow we can push through this path. So we'll just collect it on our way. And so the base step is that if we've come to T, then good, we found the path. So this one will also return the boolean whether we have found the path from S to T or not. Sorry. If we've come to T, then yes, we found the path. Great. Otherwise, we need to go through all the neighbors of U. So, for all UV edges, first we check well, okay, so I want to know that we want to construct this explicitly. Every time we'll iterate over some edges, we'll just filter out that edges we don't need. So let's do it here. So if this edge is in the residual path, so if flow in the residual network. If there is some amount of best left and there is our distance constraint. So if these two conditions are true, then this edge is in our residual path, residual network, sorry, and we can go through it. If we found the path from V, then we can just return true, and then we'll have to manually push the flow, or we can do it right here. So let's do it right here. what should we write? What should we write here? What should we do? Like, we found some path from V to sync, and now we want to update the flow on this path. So what should be here? Well, actually, we don't know what should be here because we only know the minimum on the part from S to U. Then we have the edge from U to E, and we have some path from D to T. We don't know what's the minimum of the edges on this path. So I lied to you. We'll just return not true or false, not Boolean value, but int value, which indicates how much flow we have pushed through them. So here we'll return M, since this is the minimum of edges on all our path from S to T. And here we'll just say it's equal to if it's greater than 0, then we say, then we add this flow. And we just return the same thing. What's the problem here? And if we haven't found any positive return values, then we return 0%. So what's the problem here? Is it the correct algorithm for finding the blocking flow?
Right. But it can make it faster.
Yes, this is correct algorithm for finding the blocking flow, but sadly it's the same that we wrote before. And the thing is that it's the same that we found before, and it doesn't just find the blocking path, it also modifies the current network. Well, it's not the same because of this restriction and then. So it's not exactly the same, but we can make it faster. So what we want to do here is this observation. So suppose we have come to vertex U, and we went to vertex V, and haven't found a path from V to T. What can we say about this edge? So we've called DFS U something, and we look at edge UV, and it returns 0. What can we say about this edge? Yes, so each time when when we will come at this vertex, this will still return 0. So we don't need to look at any edge twice. If we have returned 0 from this, then we can just basically remove this edge from the graph, but I'll show you how to do this a little bit more efficiently. So let's say that our graph is stored like an adjacency list, so it has, for each vertex, it has the list of edges. So E1, E0, E1. So for each vertex, we have the list of edges, and when we go through all edges, we just go through this list. So let's store for each point, for each vertex, let's store the pointer to the last edge that was visited here. So let's call it, I don't know, let's call it start B. So this is the number of the edge that we start from when we visit this vertex in the fs. So this loop will be a little different. So we'll say while there are still edges in our adjacency list, we just look for them. And is it clear what's in here? So here we just save the pointer for each vertex, and each time we enter this loop, we just go from the last vertex. So for this loop, we either go here. So if we return non-zero, then we don't modify start and just return. So for each edge, there can be multiple paths. So if we push some flow through this path, we just subtract the capacity here and do not remove this edge here, because there can be multiple paths. But if there is no path, we just remove this edge, and it's equivalent to just incrementing the pointer. So here we go. And yeah, and it's great. So now, let's consider this array again. So every time we push some flow here, we spend linear type of operations, and at least one start v increases. Because, like, if we consider the minimum edge on our path, it gets removed anyways, because it becomes, so this condition becomes false, and it gets removed. So each time we push some flow through the path, at least one start v increases. So we can, and the sum of all start v can exceed n. So this algorithm is n multiplied by n. So short summary: we want to find the flow in the network. For that, we find the blocking flow n times in a modified network, where we only leave edges between adjacent levels, and levels are defined by distance from the source in our residual network. So we find the blocking flow with this algorithm, which works in n multiplied by m, and it has the optimization if we haven't found anything from V, from edge, from U to V, then we just don't go there. So here in algorithm, before finding blocking flow, you should initialize all start to 0. And that's it for this algorithm. It works in n squared m, and it's pretty fast in practice. I don't think I had a situation where this algorithm did not work and some other algorithm worked. So it's good for almost all of the situations. So I guess I have just a tiny bit of time to explain the other interesting concept. I don't have enough time to explore it in detail, but many of you might already know that mean cut max flow duality, and that these two are equal. So what cut is that we have two special vertices again, and we have some graph. So the cut is the partition of all vertices into two sets that are joined. So they do not intersect. So this is called the cut, and we'll just say that first belongs to the first set, and the second special belongs to the second set. So this is the cut between ST or ST cut. So the cut can have its cost. So the cost of cut is 1. Is is the number of edges where one endpoint lies in S1 and the second one is in S2. There are many definitions of that. So for example, we don't count these edges as crossing the cut. So we will just need the edges that are directed from left to right. If the graph is directed, if it's not undirected, we count all directions, since there are no directions. So some U S1, B, S2, and it's just the cost of the edge. So the most important thing is how from the cut knows is that if we have graph G and we have edges, just it can be directed graph, it can be undirected graph, and the edges have costs or weights or capacities. In this context, they are the same. Then the maximum ST flow is actually equal to minimum ST cut. This is important, and this is maybe the main result of the whole flow theorems. And if you for some reason need to find the minimum cut in some problem, then you can just run max flow on the same graph and get the result. I guess I'll take a minute to. So there are basically no algorithms that solve mean cut problem, and all the algorithms that are in computer science solve max flow problem. So I'll just quickly show how to restore mean cut from max flow. So let's consider our residual network prime and run after we run the max flow algorithm on it. So we know that vertices S and T are disconnected. So there is no path from S to T. And consider all the vertices that are reachable from S by edges in residual network. So we'll say that S1 is all vertices U such that there is a path from S to U in residual network. Right. And say that S2 is all vertices So it's easy to see that this is a cut because these two are disjoint. The S belongs to first set and the T belongs to second set because it's not reachable in the residual network. And the only thing that is left to show that these two, the cost of the cut is the same as the cost of the flow. So in the residual network, it's pretty obvious because all these edges between two sets have all the edges between two sets have residual capacity of 0, because otherwise they won't be in the second set, and they will be reachable. And so the cost of this cut is 0, and whenever we get back to our initial graph, basically undoing this whole path, pushing past our graph, the result will increase by the cost, by the capacity of this path, and the mean cut cost, and this cut's cost will increase by the same. So, and if we take this theorem for granted, that's how we find the mean cut. That cost is equal to cost of max flow. No, not cost, but just max flow. And this will be the mean cut. So, to find the mean cut, you run any max flow algorithm you like, and just output the vertices in all vertices are reachable from source would be the first set, and everything else will be. So that's it for today. See you after lunch.
That's